Hello everyone, welcome to Simon. Today we are going to solve the United States Physics Team 2014 F equal to ma contest. We have 25 questions in 75 minutes, so let's start. First, a car turning to the right is traveling at a constant speed in a circle. From the driver's perspective, the angular momentum vector about the center of the circle x and the acceleration vector of the car points y, where the direction. Let's first draw a diagram. We can see the acceleration turning to the right because it's centripetal force. Then what is the angular momentum vector, which is the cross product of the radius times the velocity, which we calculated to be pointing downwards, which is e. The second question, a ball rolls without slipping down the inclined plane as shown in the diagram. Which of the following vectors best represents the direction of the total force that the ball exerts on the plane? So first we can see there is a gravitational force pointing downwards which caused a normal force. But also there is a friction force which keeps the ball rotating because friction force is pointing upward, Newton's third law will point downwards to the plane. Then we add these two forces together, we get a shape that kind of C or E. C is just the normal force, so V plus F should be number E. Right, a little bit steeper. So, question number 3. An object of uniform density floats partially submerged to that 20% of the object is above the water. A 3 Newton force pressed down on the top of the object so that the object comes fully submerged. What is the volume of the object? The density of water is 1000 kg over m cubed. So from here we can clearly note that the buoyant force increase is equal to the water expelled by the object, which when you press it completely, which requires 3 newtons, which means 3 newton is equal to 0.2 times V times density of water with times G, which is the change in volume times density of water times G. Then we can calculate V is equal to 3 over 0.2 times 1000 times 10 with G. So we have calculated in our calculator. We'll have, let me see, it's equal to 0.0015, which means times 1000, which is 1.5 liters, which is D. Okay. Question number 4. What are the correct values of the numbers in the following statements? Assume there are no external forces and take n1 equal to the mean that the statement cannot be made for any meaningful number of particles. So there are a couple choices. Then first, let's look at the first case. If a particle at rest explodes to n1 or fewer particles with known masses, then the total kinetic energy of the new particles is known. The kinetic energy for each of the new particles is completely determined. So let's first look at what if n1 equal to 1. Then we just have one particle have one energy. Then clearly we can know the velocity don't change, so we know the new velocity. What if there's 2? Then we know the conservation of momentum. They have to be equal in opposite direction. Then we have conservation of momentum equation and this conservation of energy equation. 2 equations solve for 2 unknowns, v1 and v2. It is possible. So n1 equal to 2 is okay, right? But also we need to look at what if n1 is equal to 3. Then we have 3 particles. But notice we only have 2 equations, conservation of momentum and conservation of energy. We only have 2 equations, we can never solve for 3 variables. So that's why n1 cannot be equal to 3, so n1 equal to 2. Now let's look at the second statement. If a particle is at rest explodes into n2 or fewer particles, the velocity of the new particles must lie in a line. Well, let's look at when particle is split into 2, then because conservation of momentum, the vectors have to be point equally opposite in order to cancel out each other's velocity. So 2. So but the third 3 one, it won't be a problem. It will be a problem because it won't be a single line. The 3 vectors add up together to cancel out. They have to be in a plane, not a line. So the third statement should be 3. The second statement should be 2, and the first statement should be 2. So the answer is C. Now let's look at question number 5. A unicyclist goes around the circular track of radius 30 meters at an amazingly fast constant speed of 10 meters per second. At what angle of the left or right of the vertical must a cyclist lean to avoid falling? Assume that the height of the unicyclist is much smaller than the radius of the track. So here, let's draw a diagram. Let's just use a line, straight line, to represent the height of the cyclist. So now let's draw two lines. This line is horizontal, and this line is the vertical. Let's define this angle as theta. So that's what we're going to solve, is the theta. Now let's do some force analysis. We know there are two different forces acting on this unicyclist. One is the normal force, which points directly upwards from the point of contact. Another one is the friction force, which is equal to the centripetal force. Then we know from use some trigonometry, we can know that the tangent of theta is equal to Ff over n, the friction force over normal force. And friction force is equal to the centripetal force, which is equal to m times v squared over r over mg, which is equal to, we lost the m, we need to put it up. Yeah, we can put it up. M cancelled out. We plug into a calculator, we have v squared over r times g. And let's calculate this. It's equal to 1 over 3. So what is tangent of 1 over 3? Tangent of 1 over 3 is equal to 18.4. Okay, 18.4. So the answer is C. Let's look at the sixth problem. A cubical box of mass 10 kilograms with edge length 5 meters is free to move on a frictionless horizontal surface inside a small block of mass 2 kg, which moves without friction inside the box. At time t equals 0, the block is moving with velocity 5m over s directly toward one of the faces of the box. While the box is initially at rest, the coefficient of restitution for any collision between the block and the box is 90%, meaning the relative speed between the box and the block immediately after the collision is 90% of relative speed between the box and the block immediately before the collision. So after 1 minute, the block's displacement is x from the original position, which of the following is closest to x. So this is actually pretty complicated looking. If you are trying to solve it step by step, you really want to calculate collision. But actually the collision doesn't matter, because let's look at this system, the block and the box. There is no external force on the system, so the momentum conserves, and the center of mass, the velocity of the center of mass, is constant because of Newton's first law. So all we need to do is calculate initial center of mass velocity and keep it constant for 1 minute. Then we will have our result. So what is the velocity of the center of mass of the system? We have v, which is equal to the total momentum, which is 2 times 5 meters per second, over 10 plus 2, which is 10 over 12 meters per second. That's the velocity of the center of mass, which is equal to 5 over 6 meters per second. Then times 60 seconds, we will have the distance traveled in 1 minute, which is equal to 5 times 60 over 6, which is 50 meters. So the answer is B. Pretty easy, right? So let's look at the 7th question. A 1 meters long stick with uniform density is allowed to rotate about a point 30 meters from its end. The stick is perfectly balanced with a 50 gram of mass is placed on the stick 20 centimeters from the same end. What is the mass of the stick? So first let's draw a diagram. We just draw a stick. Then we set the pivot point at 30 centimeters from one of the end. Then we know there's a mass points placed at 20 meters from the end, which means the pivot point and the mass is placed 10 centimeters apart. Then we know the center of mass is 50 centimeters. It's with the middle 50 centimeters from one end. So 50 minus 30, which is equal to 20 centimeters. Then we can use from the pivot point. Then we can use torque to calculate the mass of the stick, which is 25, which is C. Question number 8. An object of mass m is hung on a vertical spring of spring constant k and is set into vertical oscillations. The period of its oscillation is t0. The spring is then cut in half, and the same mass is attached to the system set up oscillate a frictionless inclined plane, making an angle of theta to the horizontal. Determine the period of oscillation on the inclined plane in terms of t0. So we know, let's draw a diagram. Let's see there are two different springs, identical. One is on the plane, one is on incline, one is vertical. But we notice the angle of the incline doesn't affect the period because they only affect the position of the equilibrium. And we know because the spring constant cut in half, we now have a 2k spring constant. And what's the equation of period depends on the spring constant and the mass of the system, mass of the block. Then we know the mass doesn't change, k change from k to 2k. Then we know t will be divided by a square root of 2, which is d. Okay, question number 9. A 5 kilogram object undergoes a time varying force as following graph below. If the velocity at t equal to 0 is plus 1 meters per second, what is the velocity of object at t equal to 7 seconds? So here we use the law of conservation of momentum, the impulse. Let's first calculate the total impulse and divide by the mass. We will have the change in velocity, then plus 1 will get the result. So let's calculate the area under the graph from 0 to 7. We have 3 times 3 over 2 plus 4 times 1 plus 4 times 2 over 2. The triangle plus the rectangle plus the triangle, Then we calculate it is equal to the total impulse. Okay. And then we calculate impulse divided by mass plus 1. 1 is the initial velocity, will be the final velocity. So 4.5 plus 4 plus 4 is equal to 12.5 plus 1. 12.5 divided by the mass, which is equal to 5 kilogram. So divided by 5 plus 1 is equal to 2.5 plus 1, which is equal to 3.5 meters per second. So the answer is C. Okay, answer is C. 10. A radio-controlled car is attached to the stake in the ground by 3 meters along a piece of string, and is forced to move in a circular path. The car has an initial angular velocity of 1 radius per second, and smoothly accelerate at a rate of 4 radius per second square. The string will break if the centripetal acceleration exceeds 2.43 times 10 to the 2 meters per second square. How long can the car accelerate at this rate before the string breaks? So we have a point, the string, which is 3 meters long. Then we have the car moving in velocity around in a circular motion. Then we want to know when the string will break. So we set 243 meters per second square equal to the centripetal acceleration of the car, which is v squared over r. Right? But v squared, we first want to know what is v in terms of the variables we know v is equal to vi plus at. Vi is equal to 1 times 3, and a is equal to 4 times 3, right? Because then we squared it, divide by r, we will have r, which is 3, then we have 243. Then we just calculate t. So we plug into our calculator, 3 times 243, square root it, and then minus 3 divided by 12. We will have our answer, which is t equal to let's calculate it's 2. Okay, so it's not SE. Question number 11. A point mass m is connected to an ideal spring on a horizontal friction surface. The mass is pulled a short distance and then released. Which of the following is the most correct plot of the kinetic energy as a function of potential energy? Well, there are some weird graphs down here, 5 graphs. The first, we'll just use a very simple algebra. We know the conservation energy. The kinetic energy plus the potential energy have to be constant, which means the kinetic energy have to be equal to C minus potential energy, which is a line of negative slope, right? That's very simple, which is just like y equal to k minus x. So it's E. Question number E. So question number 12. A paper helicopter with rotor radius r and weight w is dropped from a height h in air with a density of rho. Assuming that the helicopter quickly reaches terminal velocity, a function for the time which the flight t can be found in the form this, where k is unknown dimensional constants, which is like 1.164. It's just dimensionless, don't need to consider it. Then we use these as the constant exponents. So first, let's look at number 12 with determining alpha. We know that the helicopter quickly reaches terminal velocity, which means the time of flight is approximately equal to h over v, which is directly proportional to h, so we know that alpha is equal to 1 in this expression. Question number 13 is just a dimensional analysis problem. We just write out all the dimensions of the equation, then we use dimensional analysis. So what kind of dimension are there? There are time, distance, mass. Yeah, basically these three. So let's write them out. So T is equal to L to the beta times m over L cube, which is the density to the delta, times the weight, which is the force. We have dimension of mass times acceleration, ml over t square times w omega constant. Then we also need don't forget about alpha, which is 1 times l to the 1 power. Then we know, because L cancels out at the end, we only have one time. So beta plus 1 plus omega is equal to 3 delta. Also, we know the mass cancels out, so we know delta is equal to negative of omega. Then we know T is equal to 1 at the end, so W have to be equal to negative 1/2 in order for there be T equal T be 1's power at the end as a result. So we plug omega back into delta. We have 1/2 for delta. Then we plug into the first equation. We have beta plus 1 minus 1/2 is equal to 3 over 2, right? Beta plus 1 minus 1/2 equal to 3 over 2. Then we plus both sides by 1/2, which is equal to 2, is equal to beta plus 1. Then beta is equal to 1. So 13 is equal to D. Right. 14th question. A disk of moment of inertia I, mass m, and radius r has a cord wrapped around it tightly as shown in the diagram. The disk is free to slide on its side. Shown at the top of the view, a constant force T is applied to the end of the cord and accelerates the disk along the frictionless surface. After the disk has accelerated some distance, determine the ratio of the translational kinetic energy to the total kinetic energy of the disk. So we have two different kinds of kinetic energy to consider. One is rotational, one is translational. So the translational kinetic energy is 1/2 mv squared, which is equal to 1/2 times m times acceleration times t. Acceleration is t over m, so t over m times t, all of them squared. What about the rotational kinetic energy? Rotational kinetic energy is equal to 1/2 I omega squared, right? So what is omega? Omega is equal to alpha t. Alpha is the angular acceleration. What is alpha then? Right, 1/2 I alpha t squared. Alpha is equal to the torque over the moment inertia, which is tr over I times t and all of them squared, which is the final angular velocity. Then now we will have so we want to know the total kinetic energy is equal to translational plus rotational. So we add them together. There will be a total kinetic energy. Then what we want to know is the ratio between the translational and total kinetic energy. So we have 1/2 m t over m t squared over 1/2 I times tr over I times t squared. Right. Plus 1/2 m times t squared times t squared, big T and small t squared over m, right? Now we just cancel out the terms. we'll get the result. Wait, plus the translational potential energy, translational kinetic energy. Also cancel out the terms. 1/2 cancel out, t squared and t squared cancel out. So finally we get 1 over m over r squared over I plus 1/2. Oh no, no 1/2. We cancel out 1/2. Remember, so plus 1. Okay. 1 over m. Yeah, 1 over m actually. So finally we get let's multiply both sides by m and multiply both sides by r. I mean the denominator and the numerator, both sides. Multiply by m, and multiply by r, which we get is by I, which we get is I over r squared plus I. Oh, we've got m here plus I. So the answer should be equal to D. The answer is D. Question number 15. Okay. The maximum torque output from the engine of a new experimental car of mass m is tau. The maximum rotational speed of the engine is omega. The engine is designed to provide a constant power output P. The engine is connected to the wheels via a perfect transmission that can smoothly trade torque for speed with no power loss. The wheel have a radius r and the coefficient of static friction between the wheels and the road is mu. What is the maximum sustained speed v? The car can drive up a 30-degree incline, assuming no friction, no loss, and assume mu is large enough so that the tires do not slip. So first, let's draw this diagram. We have a ramp and we have a car on this ramp. Let's draw 2 little wheels and a car. Okay, this car is here. Then we wanted to drive up the incline. So first, we know that power is equal to force times velocity. Translate to the torque will be torque times omega times r squared. Then we know the power that keeping the car from sliding should be equal to force times velocity, which is F times V, right? So omega times tau times r squared have to equal to F times V. Let's first find out what is F. F is the force that's that's trying to drag the car down, with mg times sine theta and mg times cosine theta mu, which is the friction force. So we have P equal to F times V, and then we can equate the two powers together of tau times omega times r squared equal to F times V. F is equal to mg sine theta minus mg cosine theta mu, then times velocity. Oh, actually, we don't need this friction force. I forgot. In the rotational motion, we don't need the friction force. Okay, so mg times sine theta times v. So we can know v is equal to tau times omega times r squared over mg sine theta. Then we know tau times omega times r squared is equal to p, the power. Then sine theta is equal to 30 degrees, so it's equal to 2. So the answer is 2p over mg, which is A. Okay, let's look at 16th problem. First, we have question number 16. An object of mass m1 initially moving at a speed v0 collides with an object of mass m2 equal to alpha m1, where alpha is more than 1, so m2 is heavier than m1. Then it's initially at rest. The collision could be completely elastic, completely inelastic, or partially inelastic. After a collision, the two objects move at a speed v1 and v2, assuming that the collision is one-dimensional and the objects cannot pass through each other. Then after the collision, the speed ratio r1 is equal to v1 over v0. The object is bounded by which expression? This is interesting. So first, let's look at extreme conditions where it's perfectly elastic and perfectly inelastic. In these two conditions, have to be bounding the ratio of the objects, right? Because of the momentum of conservation. So we know in perfectly elastic collision, there are more momentum being conserved from object 1 to object 2, which gives object 2 a larger velocity. We know object 1 is smaller than object 2. Then partially inelastic, we have less transformation of momentum, less transform. So V1 over V2 should go up. No, actually go down. V1 over V2 should go down because less momentum transferring. And perfectly inelastic collision, the V1 over V2 should go up because there are less momentum being transferred. The more momentum it transfer, the more the less the ratio, right? So here we can calculate. Let's first calculate the inelastic condition because it's a little bit easier. So we have m1 times v0 equal to m1 plus v2, m2 times v, where is v equal to the final velocity. Actually, v1, what is v1 equal to? Is m1 times v0 over m1 plus m2. Then what is v equal to? Actually, v1 over v2 equal to is m1 over m1 plus m2. m1 is equal to alpha, m2 is equal to alpha times m1. So we have m1 divided by m1 plus alpha m1. Cancel out all the m1, we have 1 over 1 plus alpha. Then we know this is the upper bound of the equation. Then we don't know the lower bound yet. It's a little bit hard to calculate. You can calculate that, but I just lazy to do that. So R1 is smaller or equal to 1 over 1 plus alpha, bigger than something. And we see B is the only one that fits the condition, so answer is B. 17. A spherical cloud of dust in space has a uniform density, rho naught, and radius r naught. The gravitational acceleration of free fall at the surface of the cloud due to the mass of the cloud is g naught. A process occurred heat expansion that causes the cloud to suddenly grow to a radius of 2r naught, while maintaining the uniform but not constant density. The gravitational acceleration of free fall at a point away r naught away from the center of the cloud due to the mass of the cloud is now this thing. Okay. So first we know what is contributing to g naught. We know mass is equal to rho times v, right? Density times volume is mass. And we know the volume didn't change. We still want to know the gravitational acceleration from the same sphere. And according to Newton's shell theorem, we don't need to consider the gas outside of this shell. So the volume is the same. Then we just need to know how much the density decrease. We know Gm over r squared equal to G. So G is also proportional to m, and m is proportional to density. So a rho is really all we need to want to know. Because we know the volume is increased by a cube, so we know the density is decreased by a cube. The mass stays the same. So we know the radius grows by a factor of 2. So the density have to be decreased by a factor of 2 to the third power, which is g. Then we know the gravitational acceleration have decreased by 2 to the third power, which is 8, which is C, number C. Question number 18. Consider the following diagram of a box and two weight scales. Scale A supports the box via a massless rope. A pulley is attached to the top of the box. Second massless rope over the pulley and attached to the box are scale B. The two scales indicate the tension TA and TB in the ropes. Originally, scale A reads 30 newtons and scale B reads 20 newtons. So if the additional force is pulled down on scale B, what is reading increased to 30 newtons? What is the scale A shows below? This is a pretty tricky problem. And what's the problem? We just treat this box as a black box. We don't care about what the hell happened inside this box. If scale B is pulled down by 10 newton, then scale A is also pulled down by 10 newton. So scale B turned from 20 to 30. Scale A should turn from 30 to 40, each plus 10 newton. So what is the reading on scale A? 40 newtons. It's B. Tricky one, huh? So question number 19. A helicopter is flying horizontally at a constant speed. A perfectly flexible, uniform cable is suspended beneath the helicopter. Air friction on the cable is not negligible. Which of the following diagram best shows the shape of the cable as the helicopter flies through the air to the right? Okay, so here we first need to consider in a piece of rope, let's say, in a piece of rope, there are two different forces acting on it. One is the gravitational force, and one is the horizontal tension force, vertical tension force and the horizontal tension force. One is caused by gravity of the gravitational weight of the ropes below it, and one is caused by the air friction. Right. So VTV, the vertical tension, is equal to the proportional to the mass of the rope below it. Mass of the rope below it is proportional to L. And also the friction force from the air is the tension of horizontal, which is equal to the mass is directly proportional to the torque, the drag force. And the torque is also proportional to L, to the length of the rope, right? So both horizontal and vertical are proportional to the same thing. So if you divide the vertical by the horizontal, you got a straight line. So it's B. And the correct number is B. Should be A, remember? It's drag force. Question number 30. A crew of scientists have built a new space station. The space station is shaped like a wheel of radius r, which essentially is mass at the rim. When the crew arrives, the station will be set rotating at the rate of cause the object at the rim to have radial acceleration g, thereby simulating Earth's surface gravity. This is accomplished by two rockets, each with thrust t newtons, mounted on the station's rim. How long a time t does one need to fire the rockets to achieve the desired condition? So first we have a rim that has mass m and radius r. Let's calculate the moment inertia of this rim, which is mr squared, right? Then we want to have two rockets that fires t newtons and makes it rotate. So I have 2t times r, which is net torque, divided by I, which is moment inertia, is equal to the angular acceleration. And we want to rotate until the centripetal force is equal to the gravitational acceleration on the surface of the Earth. So what we want to do is we want to set v squared over r equal to g. But remember, what is v? V is equal to omega times t, right? So omega times t squared over r equal to g. Then what we want to calculate t equal to 2. We first plug in omega. Omega is equal to 2tr over I. So 2tr times t over I squared is equal to g times r. Then we square root both sides and then calculate for t. We have t is equal to square root of gr times I over 2 times t times r. Okay, then we plug in I. What is I equal to? Is I of a ring. It's equal to mr squared. And t will be equal to g times r square root times m times r squared. R squared and r cancels out, divided by 2t. Okay, so the desired outcome will be equal to A, right? Oh no, I made a mistake. I forgot to add an r after the angular acceleration. Angular acceleration times r is equal to the original acceleration. We want to know is the velocity, not the angular velocity. Okay, so let's put in r here, and we need r squared here. So r squared here, so r squared and r squared cancels out. Then we will have t equal to mg square root of mg times m over 2t, which is B. Question number 21. So two pulleys shown in the figure are made of the same metal with density of mu rho. Pulley A is a uniform disk with radius r. Pulley B is identical except the circle of r over 2 is removed from the center. Two boxes m equal to alpha times m is connected over a pulley through a massless rope and move without slipping. What is the ratio between acceleration in the system A and B? The masses of pulley A is m plus m. So first, because two pulleys are identical, we can use the same set of formula to describe them. We can use Newton's law to calculate ma is equal to T1 minus ma. A big ma is equal to big M times G minus T2. T1 is the tension on the left, T2 is tension on the right. Then we have the torque is equal to the angular acceleration times I. Then we know I times A divided by R squared is equal to T2 minus TA. What is T2 equal to? T2 is equal to mg minus ma. And what is T1 equal to? T1 is equal to ma plus mg. So Ia divided by R squared is equal to G times m minus m minus A times m plus m. So now we can use this expression to calculate A. So I divided by R squared plus m is equal to G times m minus m. Then what is A equal to? A will be equal to G times m minus m over I divided by R squared plus m plus m, right? So now we know Ia is the moving inertia of the first pulley. It's equal to 1/2 times m plus m times R squared, the moving inertia for a disk. Ib is equal to moment inertia of A minus the center ring's moment inertia, center disk's moment inertia, which is 1/2 m plus m times R squared minus 1/2 of m plus m over 4 R over 2 squared. So what that's equal to? So AA minus AB will be equal to, because the first term just cancelled out, and we switch the back and up. I hope you understand what I'm talking about. It's just algebra, you know. And we have IB over blah 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 plus blah 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 divided by IA divided by R squared plus blah blah blah. Then we cancel out all the m plus m, cancel out all the R squared, cancel out all the R's, and multiply both by R. Then we get this desired outcome. We have AA minus divided by AB is equal to 1 minus 1/2. Oh no, actually 1/4 times 1/4 plus 2 divided by 1 plus 2. And then the ratio will be equal to 3 minus 1 over 16 over 3, which is 1 over 48. 1 minus 1 over 48, which is 47 over 48, which is equal to A. The answer is A. Now look at question number 22. A body of mass m and a body of mass m much smaller than m are in circular orbits about their center of mass under the influence of their mutual gravitational attraction to each other. The distance between the bodies is r, which is much larger than the size of their either body. A small amount of matter, delta m, is much smaller than m, is removed from the body of mass m and transferred to the body of mass big M. The transfer is done in such a way that so the orbits of the two bodies remain circular and remain separated by a distance r. Which of the following statements is correct? So let's first look at the first statements. We know in a gravitational attraction, gmm over r squared. Because the bigger the difference between two mass, the smaller their product is. Just like 4 times 5 is bigger than 3 times 6, even their sum is 9. So we know the gravitational force will decrease because the smaller one is removing mass and added to the bigger one, and it's not constant. So A and B are not correct. Number C, the total angular momentum of the system is equal to m times v1 times L1 plus m times v2 times L2. What do I mean by L1 and L2? Well, it's the distance of each of the planet away from their central mass. Okay, so this is L1 is closer to the bigger m, and L2 is closer to the smaller m, and they're rotating, which their desired speed v1 and v2. And we know they're rotating with the same angular speed, so we have m times omega times L1 square plus m times omega times L2 square, which is equal to L. And we know by removing, because L1 square is bigger, is smaller than L2 square, so removing some part from smaller m to the bigger m will actually decrease the total angular momentum. You can try to calculate the equation by each minusing delta m and adding to the other side. It's going to be smaller, not going to get bigger, right? So total momentum, angular momentum of a system should decrease, not increase, and it shouldn't be constant. Okay. What about E? What about number E? Actually, we can just choose number E now, but let's see why it is the case. The period of the orbit of the two bodies remain constant. Is it? So first, let's calculate the period. Well, we know omega squared times L1. Let's use the bigger mass as a case over R, which is the centripetal acceleration. Oh no, over R, just omega squared times L1 is equal to G times Mn over R squared. Then we cancel out all the m's. We also want to know what is L1 equal to. L1 is the central mass, distance of central mass away from the bigger mass, which is mr over m plus m. And we plug this in. We have omega is equal to actually omega squared is equal to G times m over R squared times m plus m over mr. Cancel all the m, we have G times m plus m over R cubed. So we know that period is proportional to omega, and omega is proportional to the sum of two m's. The sum of two m's doesn't change by moving one of some m to the other m, so E is correct. Question number 23rd. What is the impulse delivered to the astronaut when firing the launcher? 100-kilogram astronauts carry as a launcher load with 10-kilogram bowling ball. A launcher and astronaut spacesuit have negligible mass. The astronaut discovers that firing the launchers results in the ball moving away from her at a relative speed of 50 meters per second. We know the impulse is equal to the change in momentum. The change in momentum can be the change in momentum of the astronaut or the ball, both okay. But notice we have the relative speed, not the speed according to the inertial reference frame. So assuming from the inertial reference frame the velocity of the ball plus the velocity of the astronaut is equal to 50, then according to conservation of momentum, we have negative 100. VA is equal to 10 times VB. 10 times 50 minus VA. VB is equal to 50 minus VA from the first equation. Then let's calculate what is VA equal to. So both for negative 100 VA is equal to 500 minus 10 VA. Then add both sides by 10 VA. We have negative 90 VA is equal to 500. So what is VA equal to? It's about 4.55 something. Right, 4.55555555. Always 5. And then we know VA is equal to 4.55. Then what is VB equal to? VB is equal to 50 minus 4.55, which is 45.45 approximately. Sorry. So we calculate the momentum is 45.45 times 10. Change in momentum, which is the change in impulse, will be 455 approximately. So the answer is A. Question number 24. Astronaut in the previous station is now moving at 10 meters per second as measured in certain frame of reference. She wishes to fire the launcher so that her velocity turns through as large an angle as possible. What is its maximum angle? As there's a hint, a diagram may be useful, so let's draw a diagram. Actually, it's mentioning a specific diagram here. So first, we want to use vector analysis in this problem. First, we use one vector to represent the initial momentum of the object. Then we use another vector to represent the impulse. The impulse has constant value and it can point in all directions. So trace out a circle. So let's just write a circle that represents the trace of the end point of that impulse, and use the contact point of the momentum and the impulse as the origin. Then we want to calculate the final momentum. Final momentum will be this vector, and the angle between them, the initial and final velocity, the final momentum, which is velocity to direction, is theta. So when will theta be the biggest? Well, intuitionally, geometrically, should be the impulse should be vertical to this circle, so that will make the angle theta maximum, and the final momentum should be the tangent to the circle. Then we can use Pythagorean theorem. We know, actually just use some trigonometry. We have 455 over 1000 is equal to sine of theta. So theta is equal to what? Let's plug in our calculator and see what happens. So this will equal to 27.06. So it's about 27. So C. A block with mass m is released from rest at the top of a frictionless ramp. The block starts at height h1 above the base of the ramp, slides down the ramp, and then up a second ramp. The coefficient of kinetic friction between the block and the second ramp is mu k. If both ramps makes an angle of theta with the horizontal, to what height h2 above the base of the second ramp will the block rise? So we kind of see this problem last time at 2011, right? Kind of like that, can remember. It's a similar problem, but the angle is given. And two of the ramp are both have friction. This time the first ramp doesn't have friction, the second ramp have. So we use conservation of energy. Again. So first we have initial potential energy is mg times h1 is equal to mg times h2 plus the work done by friction. The work done by friction, we first want to know this distance. Then we have mg times cosine theta times mu. The distance is h2 over sine theta. Then we just solve for h2. First multiply both sides by sine theta. We have and cancel all the mg's. We have h1 times sine theta is equal to h2 times sine theta plus cosine theta times mu times h2. Then we have h2 will be equal to h1 times sine theta over sine theta plus cosine theta mu. Then compare with the original answer, we got A. Okay. So that's it. We have finished the 2014 exam. Here we want to big thank to watching our video and American Physics Teacher Association, which produced the solution manual which we referenced.